My sincere greeting to one and all. I'm Tamanna from BSc Chemistry Junior Second Year. Today I'm here with chapter Chemistry of Actinides. As we have already learned in chapter 1, F block elements consist of two series of elements placed at the bottom of the periodic table. The two series are lanthanides and actinides, which involves the filling of 4F and 5F subshell respectively. We have studied the chemistry of lanthanides in chapter 4. Let us now discuss the chemistry of actinides. Actinides, the 14 element which follow actinium from thorium. Z atomic number is equal to 90 to lawrencium atomic number is 103 in the periodic table are called actinides. These are the analogous to lanthanides that and involve the filling of 4f orbitals. As in the case of lanthanides, the name of the series is after the name of preceding element actinium with which these elements closely resemble. These are also known as actiniums. Before 1940, only the naturally occurring actinides, thorium, protactinium, and uranium were known. The remaining elements are made artificially by nuclear bombardment. These elements are also known as man-made elements. Since these man-made elements have atomic number higher than uranium 92, they are sometimes called the trans-uranium elements. Indeed, now many man-made trans-uranium elements consist about 15% of all the chemical elements. All the actinides are toxic to humans. These elements are radioactive and therefore the isolation and characterization of these elements, particularly the heavier one, posed many problems. The individual elements are not produced cleanly in isolation, but must be separated from other. The individual elements are not produced cleanly in isolation, but must be separated from other actinides as well as lanthanides produced stimulatively by fission. The study posed serious problem due to the following reason. First, in decay processes, the emitted particles are extremely energetic, which break bond and rupture crystal structures. Second, the breaking of bonds by emitted particles in a sample of radioactive element is similar to a continuous self reduction process. Therefore, it is difficult to prove the existence of an oxidation state for every radioactive isotope. Third, the energy given out appears largely as heat in the sample. For example, the heat produced by a millimolar solution of curium, curium 242 salt in water would be sufficient to evaporate the solution to dryness in a short time. The radioactive nature has also two serious op- optional consequences. First, because of radioactive nature, it is necessary to employ or elaborate radiation shielding, and therefore, in many cases, operations must be carried out by remote control. Second, the heavier elements are produced only in very small minutes amount. For example, mendelium was prepared in almost unbelievable small amount of order of 1 to 3 atom per experiment. Therefore, it was very difficult to isolate and characterize these elements. However, the advancement in research and development of sophisticated instruments have made the chemistry of actinoid as a fantastic subject. Journal characteristics of actinoids. First, electronic configuration. The actinides involve the filling of 5f subshell. Actinium has the electronic configuration 3d17s2 from thorium atomic number 90 onward. 5f orbitals getting progressively filled because of almost equal energy of 5f and 3d subshell. There are some uncertainties regarding the filling of 5f and 6d subshells. The electron may enter either of these two subshells. Therefore, there is no doubt where thorium contain 5f electrons are not and two electronic configuration are suggested for this. Because of these uncertainties, different work have suggested different configurations. The most widely accepted electronic configuration of these elements are given in table 1. The journal electronic configuration of actinide may be written as Rn 5f1 to 5f1 to 14, 3d10 to 1, and 7s2. Probable electronic configuration of actinides. Second, physical properties. The journal's physical constant are given in table 2. Some of them these are discussed below. First, melting and boiling point. The melting and boiling point of actinides are moderately high, but they are considerably lower than those of transition elements. However, there is no regular trend in melting and boiling point values. Second, density. The density of actinoid first increases, then decreases as shown in table 2. Third, heat of fusion and heat of vaporization. The heat of fusion and heat of vaporization are measured only for a few elements. The heat of vaporization is generally decreased from Th to Am, table 2. Thorium to americanium. Third, oxidation state. Actinide shows plus 2, plus 3, plus 4, plus 5, and plus 6 oxidation state. However, plus 3 oxidation state is most common among these actinide. The different oxidation state of actinide elements are given in the table. Note: bold numbers are most common oxidation state. The oxidation state shown in parentheses are unstable. Question mark indicates species that have been claimed but not sustained. Some of the important conclusions regarding oxidation state of actinides are summed up below. First, all the actinides have a oxidation state of plus 3 like lanthanides. But this is not always the most stable oxidation state in actinides. For example, for the first four elements TH, Pa, U, and Np, plus 3 is the most stable oxidation state. It have been observed that the most stable oxidation state of the element up to uranium is one involving the valence electron. For example, the most stable oxidation state of TH, Pa, and U are TH plus 4, Pa plus 5, and U plus 6. Through neptunium Though neptunium forms plus 7 oxidation state using the valence electron, but the oxidization and the most stable oxidation state of neptunium is plus 5. Second, plutonium show all the oxidation state from plus 2 to plus 7, but the most stable state of plutonium is plus 4. Similarly, americanium show all the oxidation state from plus 2 to plus 6. However, americanium the most stable oxidation state is plus 3. For all elements after Am, plus 3 oxidation state is the most stable. Third, plus 4 oxidation state exists for all the elements from Th to Bk, and it is most important state of Pa and Np. Bk in plus 4 oxidation state is strongly oxidizing but is more stable than Pu and Am in plus 4 state due to 5 F7 configuration. Similarly, NO has plus 2 stable oxidation state due to F14 electronic configuration. Fourth, plus 5 oxidation state occurs for the element Pa2Am and is most stable for Pa and neptunium. It may be noted that M5 plus ions donate occurs in solution as such, but these ions exist as their oxocations such as MO2 positive ions between pH 2 to 4. These oxo ions are linear OM O plus and disproportionate rapidly in solution as. However, these ions are found in solid compounds. For fifth, the plus 6 oxidation state is exhibited by lower actinides as fluorides FMF6. The plus 6 oxidation state is more commonly found in the dioxo ions MO22 positive. This ion is linear OMO2 positive and is stable. It exists both in solution as well as in crystals. Sixth, the actinides form ionic species. The principal ionic species are M3 positive, M4 positive, MO2 positive, MO2 2 positive. The lower oxidation state tends to be ionic while the higher one are covalent. The general behavior of compounds or ions of different elements in the same oxidation state is the same except their tendency for oxidation and reduction. The ions MO2 positive and MO2 2 positive are stable. The dioxo except their tendency for oxidation. The dioxo ions MO2 2 positive are formed due to the high charge density. Example UO2 2 positive are formed both in solid and solid ions solution state. Oxocation are stable in acid and aqueous solution. Hydrolysis of computer in higher oxidation state give plus 5 MO2 positive ion and plus 6 MO2 positive ion. Fourth, ionic radii and actinide contractions. Like lanthanides, actinide also show actinide contraction. The size of atoms and ions of actinide decrease regularly along the series with the increase in atomic number from actinium to lawrencium. The steady decrease in the ionic radii with the increase in atomic number is called actinide contraction. The decrease in ionic radii of actinide M3 positive and M4 positive ion is shown in figure 1. The actinide contraction is due to the imperfect shielding of one 5F electron by another in the same subshell. Therefore, as we move along the series, the nuclear charge and the number of 5F electron increases by 1 unit at each step. However, due to the imperfect shielding of 5F orbitals, the effective nuclear charge decreases, which result in contraction of the size. It may be noted that in actinides construction, there are bigger jumps between the consecutive members as compared to lanthanides. This is due to lesser shielding of 5F electrons, which result in more increase in effective nuclear charge and therefore larger attraction. Fifth, magnetic properties. The magnetic properties of actinides are lesser than the theoretical predicted values. This is attributed to the fact that 5F electrons of actinides are more exposed to crystal field and therefore are less effectively shielded. The result in conjuging of the orbital contribution, the magnetic moment of tripositive actinide decrease from U3 positive to give a minimum at Pu3 positive, after which it increases and show a maximum at Cf3 positive. Thereafter it start decreasing again as shown in figure 2. Six, colors of ions. Actinide ions are generally colored. The color of the actinide ions depend upon the number of 5F electrons. The ions containing no 5F electrons or 7 5F electrons, exactly half filled F subshell, are colorless as accepted. The ions containing 2 to 6 electrons in the 5F subshell are colored. Table 4. The colors arises out of the electronic transition between various energy states within the 5F electron subshell. FF transition. The color of actinides ion arises from absorption of light depend upon F to F, F to D and charge transfer transition. The F to F transitions occur in visible and ultraviolet region and the determine the color of solution of simple actinide salts. The interruption of F to F transition of actinide is similar to the F to F transition of lanthanides. However, because of 5F electrons in actinides are more exposed than 4F electron in lanthanides, therefore these are most influenced by the ligand field and ligand. Hence, the absorption spectra of actinide complex are more complicated and are less characterized than those of lanthanides. It has been observed that in general the F2F absorption of actinide ions are about 10 times stronger and 2 times broader than those of F2F transition of lanthanide ions. It may be noted that in case of actinide ions, light of higher wavelength, lower frequency or lower energy is required to result F2F transitions as compared to lanthanide ion. This is because energy difference between 5 and 6d orbital in actinides is similar than that of 4f and 5d orbital in lanthanides. Therefore, the allowed and very strong F to D transition, even in the case of trivalent actinide ion, lie in the ultraviolet region and therefore do not influence the color of actinide ion. The allowed and higher the allowed and highly intense charge transfer transition are generally responsible for the color of actinide complex. This is found in actinides in higher oxidation state with ligand having easier oxidability. However, lanthanides do not show such transitions because they do not have oxidation state higher than 4. Seventh, formation of complexes. Like lanthanoids, actinoids also form complexes. However, actinides have greater tendency to form complex in comparison to lanthanoids. This is because of high charge and smaller size in their ions. They form a wide range of complexes in different oxidation state of actinides. Uh, 4 plus 3 oxidation state where there is not much resemblance to lanthanoid. Octahedral coordination and coordination number 9 are found. 4 plus 4 oxidation state coordination number 8 is very common. In plus 5 oxidation state, the ACF83 negative ion has cubic coordination, while in plus 6 oxidation state, the hexafluoride are strictly octahedral. The general tendency to complex ion formation is controlled by ionic size and charge and decreases as M4 positive is greater than MO2 positive greater than M3 positive is greater than MO2 positive. For ions of order of complexity ability is generally uni-negative. Bi-negative complex formed by actinides are discussed below. First, most of the actinide halides form complex ions with alkali metal halides. For example, thorium tetrachloride form the complex such as KTHCl5, K2THCl6 and K3THCl7 with KCl. Complexes of type KPF5, Na2PF7 and Na3PF8 have been isolated from aqueous media. Second, thorium tetrachloride and tetrabromide forms complexes with pyridine such as THCl4 Py and THBr4 Py. Third, actinide also form complex with pi bonding ligands such as alkyl phosphine, thioethers, etc. Fourth, actinides show complexes with acetyl, acetone, oxymine, EDTA, etc., such as tetrakis acetal acetone thorium THACAC4 and UO2 C9H6 NO22 C9H7ONO. UO2 positive form rather unstable complexes with EDTA as compared to lanthanides. Fifth, fluorocomplexes of U4, U6 are known of which N4, NH4 for UF10 is notable and it has coordination number of 10. In the aqueous solution of UO2 positive, there appears the loss of H positive form coordinates. Water followed by polymerization involving OH breathing and gives species such as UO2OH positive, UO22OH2 positive, UO22 thrice OH5 positive, etc. 6. The actinide forms a wide range of complexes in their plus 4 oxidation state. Then in other oxidation states, they form many complexes with halides and or donor chelating ligands complexes with oxo anions of all type, etc. are well known. The main fluorocomplexes are of type ACF5 negative and so on, which are nearly known as all actinides. Complexes with S donor ligand are generally less stable and more liable to hydrolysis than those of O donors. However, these can be obtained if the anion is chelating. However, these can be obtained if the anion is chelating and ionic. For example, diethyl dithiocarbamate where are the best known examples. Seventh, the boron hydrides of actinides ACBH44 are also known as therium, urium, platinum, neptunium, and palladium. ACF4 plus 2 AlBH4 thrice ACBH44 plus 2 AlF2BH4. These compounds are isolated. These compounds are isolated by sublimation from the reaction mixture. These complexes fall into two types. A. Boron hydrides of Neptune and Pu are unstable volatile monomeric liquid which are at low temperature crystalline with 12 coordinate structure similar to ZrBH44. B. The boron hydrides of THPA and U are thermally more stable and less reactive solid. These have Haeckel polymeric structure having bridging group. Eighth, actinides also form organometals compounds such as carboxyl, cyclopentadienyl, and to lesser extent cyclooctatetraenylene, cyclopentadienyl of the type and derivatives of the type AC4N5 minus C5 H5 thrice X, where X is halogen atom and alkyl or alkoxo group of BH4. Eighth, reactivity. The actinides are electropositive and very less reactive. Sorry, are very reactive metals. The reactivity increases with increase in atomic number. The direct reaction of actinide with oxygen, halogen, and acid are similar to those of lanthanides. They react with hydrogen to form non-stoichiometric hydrides with the formula MH twice or MH3. They readily turnish into air, forming an coating of oxidation oxide, which is protective in case of H burette, but less so for other elements. These metals react with more non-metallic, especially when heated. They resist attack of alkalis and are less reactive towards acid. The chemistry of actinide is mainly concentrated on uranium and to the lesser extent on thorium and plutonium. Ninth, compound of actinides. Actinide form many compounds with known metals. Some of the important compounds of actinide are discussed below. Oxides and chalcogenides. Actinide form oxide in different oxidation state of plus 2, plus 3, plus 5, and plus 6 oxides of actinides and are refractory material. THO2 has the highest melting point 3390 degrees Celsius of any oxide. These have been actually studied before of their important as nuclear fuels. Dioxide are known for almost all actinides. The general preparation of by ignition of the appropriate oxalate or hydroxide in air. The exception are CmO2 and CfO2, which requires O2 rather than air, and PaO2 and UO2, which are obtained by the reduction of higher oxides. For example, UO2 is obtained by the reduction of U3O8 and with CO. It has black reddish brown color. The only anhydrous trioxide is UO3. It is obtained by heating uranyl carbonate or uranyl nitrate at 400 degrees Celsius. Among the tetrahalide, tetrafluoride are known for the element up to Cf. They are also formed by the heating of dioxides in HF. In presence of H2 or O2, they can also be prepared by heating the corresponding trifluoride with F2. In all these cases, metal is yet coordinated, having slightly distorted square antipremastric array of F negative ion. Occurrence and isolation of actinide elements. All the actinide elements have unstable nuclei and undergo radioactive decay. Among these, the half-lives of 2U3TH, 235 uranium, 238 uranium, and possibly of 244 plutonium are such that they have remained on the Earth since the formation of the solar system. TH and U are the known by no means rare and make up 8.1 ppm and 2.3 ppm of the Earth crust, respectively. These are in fact more abundant than tin. Let us briefly discuss the occurrence and isolation of uranium from its natural sources and some other elements obtained from uranium. Occurrence and extraction of uranium. Occurrence. Uranium occur in the following minerals. First, pitch blend contain mainly uranium as U3O8 along with complex silicates of uranium, radium, thallium, thorium, PBBI, etc. Second, carinoids K2O into 2UO3 into 2 into V2O5 NH2O. Third, Atonite CaUO2 twice PO4 twice H8H2. Fourth, calcium caronite CaO into 2UO3 into V2O5 NH2. Extraction of uranium. The main source of uranium is pitch blende. It can be extracted through the following steps. First, concentration. The pitch blende ore is crushed to a fine powder and concentrated by gravity separation method to remove unwanted lighter impurities. Second, roasting. The concentrated ore is roasted in the reversibility furnace in the presence of excess air to remove sulfur, arsenic, and other volatile impurities. The roasted ore, which contains U3O8, is fused with sodium carbonate and sodium nitrate. The whole mass is then added to fuse, resulting in formation of sodium uranate. Third, leaching the sulfur acid. The fused mass of leached with the dilute H2SO4 so that sodium uranate changes into soluble uranyl sulfate with while impurities such as PbSO4 and RaSO4 remain insoluble and are filtered off. Fourth, treatment with sodium carbonate. The solution is treated with an excess of sodium carbonate when impurities such as aluminium, nickel, cobalt, and manganese get precipitated as basic carbonate while uranium remain in the solution as sodium tricarbonate uranate. Fifth, treatment with sulfuric acid. The insoluble carbonates are filtered off and the solution is neutralized with dilute sulfuric acid and evaporated to dryness when sodium diuranate N2 use 2O7 is obtained as a heavy yellow precipitate. 6. Treatment with ammonia carbonate. The yellow precipitate of sodium diuranate is digested with ammonium carbonate resulting in the formation of soluble ammonia uranyl carbonate. The insoluble impurities are filtered off. The filtrate is boiled when lemon yellow crystal of ammonia diuranate NH4 twice U2O7 are obtained. On calcination, ammonium diuranate give uranium oxide U3O8. Alternatively, the roasted ore after step 2 is heated with dilute sulfuric acid for above 6 to for about 6 to 24 hours in the presence of an oxidizing agent such as MnO2. These oxidize the U3O8 present in the roasted ore to the soluble uranyl sulfide. When ammonium carbonate is added to the solution, ammonium uranyl carbonate NH4 twice UO2 CO3 thrice is crystallized out with an ignition gives U3O8. Production of uranium from U3O8. Uranium can be obtained from U3O8 by the following method. First, U3O8 is reduced to uranium dioxide UO2 by heating with charcoal or hydrogen. Second, UO2 is heated with hydrogen fluoride to get uranium tetrafluoride UF4. UO2 plus 4 moles of HF heated at temperature 400 to 500 degrees Celsius give UF4 plus 2 moles of H2O. The uranium tetrafluoride is reduced by heating with magnesium or calcium in presence vessels. Alternatively, UO3 is heated with chlorine to form yellow crystals of uranyl chloride UOCl. This is on heating with carbon in the presence of chlorine give volatile uranium tetrachloride. This is on further heating with sodium metal give uranium metal. The flow sheet diagram for the excretion of uranium from the pitch blende is given below. Chemistry of separation of neptunium, plutonium and americanium from uranium. These are the product mainly from uranium in nuclear reactors. Natural uranium contain a large portion of 238 uranium, whereas 235 uranium is present only to the extent of 0.7%. In the nuclear reactors, the interaction of slow neutrons with uranium present in natural uranium gives rise to these elements due to the nuclear reaction. Americanium can be obtained by succession of N or gamma reaction starting with Pu in the nuclear reactor. The yield of the heavier element is controlled by two factors. First, the half-life of various isotopes. Second, by their ability to absorb neutrons. These elements are extracted from spent fuel rods which have been used in nuclear reactor. However, it is more may be noted that their separation is very difficult and hazardous. This is because they are not only mixed with highly radioactive fission product, but the material is also feasible. Moreover, Pu is extremely toxic and carcinogenic. The reprocessing of nuclear fuels is an important new technology. In addition to Pu, Np, and Am, the irradiated nuclear fuels contain isotopes of over 30 fission product elements. Some of these are second transition elements I, X, cesium, Ba, SrCa, and lanthanides. The excretion of neptunium, plutonium, and americanium involves the following procedure. The solution of waste product and concentration of these stored the double walled stainless steel tank sealed by concentrated air is extracted from the reactor's waste. Later actinides, the elements from curium onward, curium, berkelium, californium, einsteinium, fermium, mendelevium, nobelium, and lawrencium are called later actinides. The isotope 242 cm was first isolated among the product of alpha bombardment of 239 Pu and its discovery actually proceeded at americanium. This is available in microscopic quantity while all the other are available only in tracer amount. Isotopes of other elements were first identified in product from the first hydrogen bomb explosion 1952 or in cyclotron bombardment. Much less is known about this element because of their limited availability and their instability. The chemical interest in these later actinide element is mainly used their resemblance with the corresponding lanthanides quite closely. However, in spite of their similarities, these actinides can be easily separated from the lanthanides because they form complex more readily. For example, with concentrated HCl, they form complexes more readily. When both groups of ions are observed on cations exchange column, the anthenides can be elated. With concentrated HCl, the actinide ions are separated from each other by the ion exchange using nitrate solution of elated them. The order of among The actinide ions are separated from each other by the ion exchange using nitrate solution to elevate them. The order in which the actinide ions are elated shows a close similarity to the order in which the lanthanides are elated. Like lanthanides, the plus 3 oxidation state is the most stable for the all elements from atomic number 96 to 103. CMBK, CF, ES, MD, and LW except number. The most stable state of NO is plus 2 because it is a favorable F14 electronic configuration. The elements from 98 to 102 like californium to nobelium show plus 2 oxidation state also. Except from nobelium, this state is strongly reducing in nature. However, higher oxidation state of plus 4 are also found in Cm and other elements. Lawrencium exists only in plus 3 state and resists both oxidation and reduction. The oxidation state of later actinides are similar to lanthanides. This can be seen by comparing Cm and Gd, Bk and Tv, No and Yb and Lr with Lu. The, uh, spect- the spectral and magnetic properties of some compounds of isoelectronic pair of ions such as CmF3 and GdF3 are also similar. This is due to the almost similar amount of energy required for the promotion of 5F to 6D in later actinides. As in the case of lactinide, 4F to 5D, however, form the earlier actinide up to americanium. Less energy is required for the promotion of 5F to 6D than for 4F to 5D promotion of lanthanides. Possible new elements. Until 1970, it was thought that the practical limit of the periodic table would be reached at about 108 elements. It have been theoretically calculated that the half-life of the element will decrease about further as new elements are discovered so much that the half-life of the longest. It has been theoretically calculated that the half-life of these elements will discover further as new elements are discovered so much that the half-life of the longest lived isotopes of the element beyond element 108 would be very short. Due to spontaneous fusion decay, therefore, it will be more difficult to synthesize the study the chemistry of element beyond atomic number 108. However, these theoretical calculations did not discourage the scientists and they were successfully in discovering element up to atomic number 112, which makes the completion of actinide series at 5F subshell, which is completely full at element with atomic number 103, and the 3D 6D subshell with atomic number 112. Even special stability is predicted for element with atomic number 114. Today we have discussed element up to 112 element. These elements were earlier named traditionally by its discoverer or discoverers. Some elements like uranium and neptunium were named based on the names of planets. The name of Rutherfordium and Lawrencium was based on the name of two renowned scientists, while the name of some elements like Bricklinium, Californium were based on the place of their discovery. Later on, it was found that some of these elements were discovered simultaneously in different laboratories, and different names were suggested for them by their discoverers. Therefore, after several years of discussion by the Commission of Nomenclature of Inorganic Chemistry (CNIC) and comments of chemists around the world, IUPAC in 1997 gave the approved official name of four elements with atomic number 104 to 109. However, the name of the elements with atomic number 110 and above yet not be officially announced. To solve the problem, IUPAC recommended a nomenclature to be followed using these new elements until their names are officially recognized. The nomenclature is based upon the Latin word from their names numbers. For example, nil for 0, un for 1, and so on as shown in table 6. The names are derived by combining together the roots in the order of digit with make up the atomic number and union in added at the end. For example, the atomic number 104, the name may be written as unilqualium, and is assigned the symbol UNQ. The UPSC name of some element more than 100 are given below. Thank you.